welcome everybody. So, this is the first lecture for the boundary value problem, this course. So, now here what we will be doing is boundary solving solution techniques for boundary value problem involving both ordinary differential equations and as well as partial differential equations. So, first we will start with the simple one, ordinary differential equations. That means the independent variable is single. So, now before that little bit of discussion on some not exactly prerequisite, some preliminary concepts which we will be using in the solution techniques. Now, one of these is that we will come across several complicated function. So, complicated function which may have a piecewise discontinuity. Piecewise discontinuity means, say at any point piecewise discontinuity. So, what it implies that at any point say C, now at this point a function, if you approach from this side, that means is the increasing side. So, this we call say a C minus, and if I approach from the other side, that is we call as FC plus. So, if these are not exactly equal, both are valid, so but it is not exactly equal, so then it is a jump discontinuity. So, any step function, say some function which is some value say at 1 given by say f is like this is x, and at say f is say x for 0 less than x less than 1, and it is say half. I can say no, this is 1. So, this is 1, say 1, and this is half for 1 less than x less than some other value, infinity or something, so less than equal to 1. So, that means from 1, so this is half. So, if I approach from here, f value is half at the point 1, from here if I approach, that is 1. So, there is a jump discontinuity is occurring. So, this kind of piecewise discontinuous, or if it is continuous, continuous means both y's it is same, both fc minus equal to fc plus. But this kind of function is still integrable. It may not be differentiable, but it is integrable. Now, we may come across this kind of function. Now, one of the simple way is to express this function in terms of a smooth functions, that is well behaved function. So, one of these is called the Fourier series. So, Fourier, I believe is a French engineer. So, basically Fourier started this Fourier series, he developed the Fourier series for solving the heat transport equation. Now, in the Fourier series, now say that is one of the kind. So, in general we can say suppose in interval AB, in a say any interval AB, let a set of function phi x, say I equal to 1, 2, etc., they are orthogonal, a sequence are orthogonal. So, orthogonal means what I have is orthogonal in AB, in the interval AB. So, that means the inner product of these two functions phi x ix and phi jx dx is equal to delta ij, that is the usual. So, we can write this as phi I phi j, which is called the inner product or dot product of these two functions. If delta ij means it is equal to 0 if I not equal to j, and this is 1 if I equal to j. So, if this kind of situation occurs, so then it is referred as the orthogonal function. So, if that is the thing, then f x can be expressed as a linear combination I equal to say 1 to infinity C I phi I x in terms of this function. C I are undetermined yet undetermined function, undetermined coefficients, which can be determined through the orthogonal properties. So, this expansion. Now, what is the advantage? That if the fx is jump discontinuity is there, so but may not be differentiable, but what I have here in this series, it's well-behaved function, because this phi I x can be a smooth function, differentiable and everything. So, I can express fx in terms of a series of differentiable functions. So, that is the advantage. Now, Fourier, what he did, he explored the condition, this say the sine function, sine x, cos x, they are orthogonal. So, orthogonality of this function, orthogonality of these functions. So, sine let us call Lx, so some coefficient, so orthogonality. And from there, what I can write a Fourier series, say let a function fx, if I represent by this way, a0 by 2 plus sigma n equal to 1 to infinity n cos n pi x by L plus bn sin n pi x by L in rather I would say is the Fourier series representation of fx in minus L to L within this zone, Fourier series representation in minus L to L fx. So, where a0 I can be obtained as 1 by L minus L to L fx dx, where these are called the Fourier series coefficients, an equal to 1 by L. Again, this is all by the orthogonality property of the sine function and cosine functions, and Bn can be written as 1 by L minus L to L fx sin n pi x by L dx. Now, so within the interval minus L to L, so what we have assumed that the function fx is periodic with period 2L. So, that means we have extended the function fx beyond minus L to L by this manner, fx plus 2L is equal to fx. So, by that way extend, or rather I would say the function is extended, the function fx is extended beyond minus L to L by considering it a periodic function. Now, this minus L to L can be replaced to any other, say minus pi to pi or 0 to pi and other by simple transformation. So, now one important thing is that the function fx, it can have discontinuities. So, but the function to be, the important thing is that the function fx, the fx should be integrable. in minus L2L. This is the only requirement, that the function has to be integrable. No need for any differentiable or continuity and other things. What I need is the function to be integrable within the interval minus L2L. If that is the thing is occurs, if that is the thing is guaranteed, then this A0, A1, A0, A1, A2, AN, and etc. B0, B1, B0 is 0, Bn, etc. can be determined. And how the summation behaves is that we can say that if fx is integrable, so fx equal to the summation of this. So at any point, fx and the function value are same. So I can say this way: the Fourier series converges to fx at all points where fx is continuous. If x equal to c is a point of discontinuity, of fx, but still integrable, then the sum of the Fourier series, then the Fourier sum of the Fourier series is can be written as half of fx at c, not x. So f c plus f c minus. So we know that both, because it is only allowed is a jump discontinuity. If you have a situation where the function is integrable, need not be differentiable. So in that case, you can only allow a jump discontinuity. So the Fourier series will converge to the average of f c plus and c minus in this case. Okay, so that is about the Fourier series, which concept has been introduced in the subsequent discussion for solving the boundary value problem. Another important thing is that partial differential equation. So obviously, I am not here to talk about all the characteristics of the partial differential equation. I am just in classification of partial differential equation, how we classify that one. Now, partial differential equation means what we have is a function u, say, if it is a more than one variable. So if you have a more than one variable as independent variable, then a PDE arises. That means you have ux, uy, uxx, uxy, etc. So this kind of things appears. So these are called the partial derivative. So instead of the ordinary differential equation. So a situation which involved, so a PDE can be written as second order PDE, say ux, let me write this way, uxy, uyy, ux, uy, uxy equal to 0 is a general form of a second order PDE. A general form of a second order PDE, any combination, f is any function, a known function. Now, if I consider a PDE given by this a uxx plus a 2b uxy plus c uyy plus say some small f which contains all these first order and u and etc., where a, b, c are function of xy or constant. It can be constant or function of either x or y, or not all 0, all cannot be 0. So, then the second order PD have a linear principal part. So, that means the principal part, which is the second order part, is linear. So, in that case we can make some classification which resembles with the ordinary the conical equations. So, resemble with the equation second order homogeneous equation for conics, second order equation for conics, we can classify as if b square minus ac is greater than 0, this is called the hyperabolic equation. Again, it has nothing to do with the solution form. It is just a resemblance with the second order conic equation. So, if you have a second order homogeneous conic equation for the conic, so which are termed as the hyperabolic if b square minus ac greater than 0. So, classical example is this equation utt minus c square equal to uxx, wave equation. This is referred as the wave equation. Any kind of wave propagation which is governed by this second order hyperabolic equation. Same way, if v square minus ac equal to 0, this is called the parabolic PDE. Parabolic PD. Classic example, ut minus sigma uxx equal to 0. We will be talking about this equation, how to solve this kind of equations in the subsequent lectures. So, that is why I am introducing it here. We have termed this as a parabolic equation. So, it is a heat conduction equation, heat conduction equation. It is a very well known equation which have these characteristics. Then third case which can be is b square minus ac less than 0. These are termed as elliptic PDE. Elliptic PDE. So, one of the I think I have not written clearly. One of the example of elliptic PD is this Laplace equation or Poisson equation. So, that is del 2u del x2 plus del 2u del y2 equal to fxy. So, this kind of any diffusion process is governed by this way. So, this is a boundary value problem. This is a pure boundary value problem because x, y are the space coordinates. So, it has a definite boundary. So, our emphasis will be this class of PDEs, because this class of PDEs are the forming the whole many in mathematical modeling we come across either a hyperabolic type PDE, parabolic PDE and elliptic PDE. Now, the way we have defined, so it is very obvious that the nature of the equation can change as x, y are varied. So, when the domain is varied, so we can have the nature of overlap. That means a which was hyperabolic, it can be elliptic, it can be parabolic and so on. Now we will talk about how to solve the boundary value problem by the Strum-Liouville problem will be discussed. I will be now talking about the boundary value problem, how to deal with the boundary value problem with those preambles, whatever we talked in the previous lecture, the importance of the boundary value problem in solving several mathematical modeling and engineering problems and realistic situations. Now, boundary value problem, as these statements suggest, that there is a boundary. So, all the conditions are to be imposed in different boundary points. So, we can define a boundary value problem by this manner. Boundary value problem we call as abbreviation as BVP. So, a differential equation now this differential equation can be a ordinary differential equation or partial differential equation that has data given at more than one value of the independent variable is a BVP. So, thus BVP must be at least second order. At least second order. Second order. It can be higher as well, that is not a issue. Say for example, one of these boundary value problem we can write say d2y dx2 plus y equal to say some f(x) and x is varying from a to b, and the conditions are two conditions, second order equation. So, two conditions are given at two different points ya and yb, say yb. So, obviously, this is the situation that you have a variable x is varying from a to a point another point b, and what you have is given is the y, and y say suppose at this point y is given some value y a, and it is taking some value at say this is the point, let us call b. So, this is your byb. So, this kind of situation, so this is x axis. So, this kind of situation is referred as the boundary value problem. Now, in the contrast to initial value problem, which are relatively easier to handle, initial value problem, which abbreviated as IVP. So, in the IVP, what happens is all the conditions are given at a single point. All the points, all the conditions, whatever the conditions are imposed, they are imposed at a single point, and that point is referred as the initial point. So, for example, d2y, normally this will be of time derivative. So, sine hyperbolic t. So, all the conditions say y0 is given to be some value and y dash 0 is given say some other conditions is prescribed. So, two conditions, one as a function value at t equal to 0 and the function derivative at t equal to 0. So, let us call this y0 and y dash 0. Now, this IBP has a advantage is that one can reduce the initial value problem to a single first order ordinary differential equation or first order differential equation. So, for example, if I have a nth order IBP, so suppose your equation is given like this way, dny dx n equal to say f some function of x, y, y dash, y n minus 1th derivative. So, we have a nth order ODE, nth order ordinary differential equation, and the conditions are all given conditions. So, since it is a nth order ODE, so we need n conditions. So, n conditions, n number of conditions are prescribed at a point x equal to 0. Say. All the conditions are prescribed at a single point, that is at a single point. X equal to 0. It can be any other x equal to 0 or x equal to L or x equal to whatever, we can bring it down to x equal to 0. Now, the advantage is that now if I do this simple manipulation, that is, suppose if I define say z dash equal to rather first we let us say z. So, let us call z equal to dy dx, then say w equal to instead of this way, because over will be exhausted with the alphabet. So, let us call this is say y1. So, if I call y1 is dy dx, y2 is dy1 dx, y etc. So, dy1 dx, so in other words it is y double dash. So, y3 if I call as y2 dash, so basically this is y triple dash, and like that way. So, I can go up to say y n minus 1, which is basically d n minus 1 dx n minus 1. So, if I substitute, let these are the variable we introduced. We have introduced the variables, n number of variables, n minus 1 number of variables, y1, y2, y3, yn minus 1 and our y. So, if I now substitute there, so what I get is d n y dxn becomes y n minus 1 dx. So, there should be, this is n minus 1 I mean. So, y n minus 1 dx equal to f x, y, y1, y2, etc., y n minus 1. So, this constitute n first order, which are n number of n first order ODE. In this case, it is ODE because y is depending on a single variable, independent variable is x only. So, and accordingly our conditions can be expressed in this way. Say all these conditions, what the conditions which was prescribed is, all the conditions are prescribed at x equal to 0. So, the conditions say it is given like this way, y0 initial condition we call as initial, okay, I think I should rub this. So, let us call this is initial condition. Initial conditions are, which are given is y0, say some value y dash 0. say let us call as y0 dash etc. y n minus 1 at 0, that is the n minus 1 derivative. We call this as n minus 1, like that way. So, these are the n initial conditions, n conditions. N conditions are prescribed to solve this nth order ordinary differential initial value problem. So, this along with these 1 and 2 are the constituting the IVP. And now this IVP, what we are doing is, we have introduced n minus variable, n minus number of variables like y1, y2, yn minus 1, and with that we have constructed n first order ordinary differential equations with conditions given by y0 is y0, y1 0 is y0 dash etc. This is n minus 1 0 is equal to y0 n minus 1. So, these are the initial conditions are, so n conditions and n, so these are the n number of conditions are reduced. So, basically we can say a system of which forms a n number of first order IVP. Yeah, it is coupled, they cannot be separated out, we cannot take out one and solve and separately. So, they are coupled, solution of y1 is depending on y, solution of y2 is depending on y1 and so on. So, they are coupled set of n first order initial value problem. But obviously, this is not possible, this trick does not work for the boundary value problem, because as we have defined the boundary conditions, say for example, even for the second order boundary value problem, here we have the conditions at two different points ya and yb, even these tricks won't work over here. So, that means the boundary value problem cannot be reduced to a first order situation. So, we have to handle at least with the second order differential equation. Now, first we start with the homogeneous boundary value problem. Now, homogeneous means we have all the terms are depending or involving the variable y. There is no term which is independent of, or rather no term which is free of y are involved. If there is some term which are free of y, then that becomes a non-homogeneous situation. So, first we talk about the homogeneous, and first this can be classified in a form which is termed in the name of Strum-Liouville. So, we consider this Sturm-Liouville problem. Yep, this is now. This is in general classified as Sturm-Liouville problem. So, we define a operator LU by this manner minus ddx of px say du dx plus QXU equal to say lambda a constant U. And this is the operator, we call this operator as LU. So, this can be expressed in this way, LU equal to lambda U. And boundary conditions are given by this manner. Say alpha 1 U, and let us take the x is varying from 0 to say a. It can be a to b, but I can make a shift and reduce the situation between 0 to a. So, we can put in this way alpha 1 u 0 plus say alpha 2 u dash 0 equal to 0 and beta 1 u 0 u a plus beta 2 u dash a equal to 0. So, again this is a homogeneous boundary condition, homogeneous BC. So, we have a homogeneous equation given by this way, LU equal to lambda u and homogeneous boundary condition. And this alpha 1, alpha 2, beta 1, beta 2 are such that these cannot be, let us take these are all positive and not all 0. So, if I put this condition, that means it cannot be all positive. So, if we take alpha 2, beta 2 equal to 0, alpha 2 if alpha 2 and beta 2 equal to 0, alpha 2 and beta 2 equal to 0. So, in that case this is called the basic usual again beta 2 I mean. So, that means there is no derivative in the boundary condition, this u dash 0 or u dash. So, only you have a prescription for u 0 and u a. So, this is called the Dirichlet BC boundary condition in that case. And if alpha 1 equal to beta 1 and both are 0, this is called the Neumann boundary condition. And if both are present, so then call it the general one, we can call that Robin boundary condition. So, Robin condition. So, these names are not very important. So, in other words, what we have is a combination of function value along with its derivative in a combination form. So, either way we can have only the situation where the function value is given or its derivative is given, or can be in a both form. So, obviously, what we can see is that this is a equation 1 and this is boundary condition as equation 2. So, this is a homogeneous Sturm-Liouville problem. So, u is a 0 is a solution. So, u 0 is a solution and we call this solution as the trivial solution. So, basically what we are looking for now, how to find out a non-trivial solution for this kind of things. That means, to find u not equal to 0 or non-trivial solution. Now, first few property or few characteristics of this Sturm-Liouville problem or this operator L, we can look into it. One is this operator is self-adjoint. That means, suppose you have two u and v they satisfy the boundary conditions. They satisfies BC given by 2, BC2, then what we have is A to B Lu-V dx equal to A to B U-Lv dx. So, as we have discussed introduced in the very beginning, that this can be stated as the inner product. So, that means Lu-V, this is the inner product in domain A to B, and this can be written as U-Lv. So, if their operator is such, then we call this operator as the self-adjoint operator, and it is very easy to say that. So, what we have chosen is that U-V to satisfy the boundary conditions. Now, this we can write as sigma A to B lambda U-V dx, and in the same way this is also can be written as A to B, because Lu equal to lambda U, so we get lambda U-V. So, this implies these conditions. So, this operator, one can say that they are self-adjoint. Then another characteristics of this operator is given by this way. This is called the Lagrange's identity. Again, the name is not important to remember, only these characteristics are important to keep it in mind. So, U-L-V minus V-L-U equal to P-U-V dash minus V dash U, no, U dash V. P-U-V dash minus U dash V derivative. So, if I can say that this is a constant. So, in other words, this implies that if U-V are satisfying the Sturm-Liouville problem, then we can have that this is as constant, because this side is 0. Now, what we get from here is U-L-V minus V-L-U equal to U ddx of P, this is V, so V dash minus, or what we have is plus Q V. Now, in the operator we have introduced here is a minus sign, so that can be minus, and without that also there is a sometimes it is customary to consider this minus sign. So, if we keep this minus here, and then we have V, and this is minus ddx of P U dash plus Q U. Now, if we do the operation here, so what I get here, this U, Q, U, V, so these terms are cancelled out, and what we left is minus U minus U P V dash dash minus, so plus V P U dash dash, and this is becoming U into P V double dash U into P double dash plus P dash V dash minus V into P U double dash plus P dash U dash. So if we do this manipulation, so finally we will get a situation as because what we will have is P dash will be there, so P dash will be there. So what we have is P dash into what we have here U V dash and minus V U dash and plus P into U V double dash and minus V U double dash. So this together can be said as P U V dash minus V U dash derivative, because the other term will get cancelled automatically. So this is the two important characteristics of this non-homogeneous Sturm-Liouville problem. Now, before we leave for this part, so I just introduce what is called the eigenvalues and eigenfunctions. Now, what we have found eigenfunctions of the this Sturm-Liouville problem. Rho um. So basically, this L is a linear operator and it is leading to LU. When it is operated on U, we get a we are getting back this term lambda U. So we call this lambda as the eigenvalue of L, of the operator L, and corresponding to this lambda, to this lambda, corresponding to this lambda, the solution U is called the eigenfunction. Now, obviously, what of course, it is subject to a certain boundary condition, subject to boundary conditions. So, as usual, the boundary conditions. So, lambda is the eigenvalue. Now, given lambda, we can solve this subject to this solution of solution U. So, solution U means it is not only satisfying this equation, it is also satisfying the governing boundary conditions. So, so this U must satisfy the not only this equation, is also satisfying the given boundary conditions. So, if U is non-zero, or non-trivial, then this u is the eigenfunction corresponding to the eigenvalue lambda. Let us call this, instead of here, this u is always, can be 0 is a solution, 0 is always a trivial solution. So, this eigenfunction when non-zero solution. So, we call the eigenfunction provided u is non-zero over there. So, we stop for this one, for this lecture now. We will continue next.